Hello again. We are back in GEM Juices, but today we will see a different problem. Today we will talk about a problem called multi-period inventory problem. As I mentioned before, a part of the customer's request to GEM products for some special celebrations. However, another very important part of our sales are the products that we have created, and that we sell regularly in our stores. Depending on the season, some products increase their demand, and since we get the juices of different fruits, there are also seasons where some fruit decreases their prices. When this happens, we try to increase the production of this juice in order to increase our profits. Obviously, we have an established production capacity, and sometimes we cannot process all the juice we want. On the other hand, we also consider that these juices need to be refrigerated for later consumption. And as you may assume, storage is also limited. In addition to our storage restrictions, you should also consider that this cooling process generates costs, and these costs will decrease our profit. Go back to the office, and there, I will show you the data relevant to the problem we are facing. Very good. Let me show you the relevant data. This table shows the projections of GEM about the demand and cost for this particular type of juice during the next 6 bimesters. The sale price is constant throughout the year. Each liter of juice is sold at $2.70. The factory has a production capacity of 2,500 liters per bimester. And our refrigeration area has the capacity to store 3,500 liters. This capacity includes the material that is produced and sold in the same period. Finally, for each liter of juice that is produced in a season, and stored for later use, a storage cost of 10 cents per bimester is incurred. Let me define our decision variables as Xij equal to the number of liters produced in the bimester I, and sold in the bimester J. This expression makes sense only if I is less than or equal to J. For example, it would not make sense to say that we are going to produce in the bimester 4, to sell in the bimester 2. On the other hand, it is also convenient to say that for GEM it is not obligatory to satisfy the projected demand. Think about the objective function. We are interested in maximizing our profit. For each liter produced in the first bimester and sold in the first bimester, our profit will be 90 cents. This is because our cost of production is $1.80, and we sell it at $2.70. For each liter produced in the first bimester and sold in the second bimester, our profit will be 80 cents. This is because our cost of production is $1.80, and we sell it at $2.70. But we must pay 10 cents because it remained a bimester in our warehouse. For each liter produced in the first bimester and sold in the third bimester, our profit will be 70 cents. This is because we must pay storage costs for 2 periods. Continuing with this reasoning, then we will earn 40 cents for each unit produced in the first bimester and sold in the sixth bimester. Rewriting this expression, we conclude that the first 6 terms of the objective function are. Now think about the units that are produced in the second bimester. We will have a profit of 60 cents per liter we produce in the second bimester and sell in the second bimester. This is because the cost of production is $2.10 and the selling price is $2.70. For the units we produce in the second bimester and sell in the third bimester, we will have a profit of 50 cents, because we must pay 10 cents for storage. In the same way, we can deduct the profits of the following variables. Now, you will get the profits of those liters that are produced in the third bimester. And we can continue this way, until we get the expression that represents our objective function is the following. Now, we must think about our constraints. We will have constraints about the production capacity, storage capacity, and demand. Our production capacity is 2,500 liters per bimester. Therefore, in the first bimester our production must be less than or equal to 2,500. This constraint can be formulated with the following expression. In the same way, we express the other constraints on our production capacity. Now, think about our storage constraint. Remember that our capacity includes the material that is produced and sold in the same period. I think that for the first bimester, the constraint is easy to formulate. For the second bimester, you must consider the units that we have stored in the first bimester, and those that are produced and consumed in the second bimester. I hope you can deduce the following expression. For the third bimester, you must consider the pieces that were produced in the previous bimesters. And so on. Now, we just need to express our demand constraints. Because GEM is not required to meet projected demand, then the first constraint will be as follows. The second constraint will be the following expression. And so on. Finally, let me write the complete formulation. The solution is. As you can see, we must produce 2,500 liters the first bimester, produce 2,200 liters the second bimester, produce 700 liters the third bimester, produce 2,500 liters the fourth bimester, produce 2,500 liters the fifth bimester, and produce 900 liters the sixth bimester. There are other ways to formulate this problem. Let me show you a different way to do it. We will put the tables back with the information. But now we will define our decision variables in a different way. Let Pi be the number of units produced in period I. Let Si be the number of units sold in period I. Let Hi be the number of units stored at the end of period I. This is the classic way of formulating this kind of problem. Remember that we want to maximize our profit. We will express our profit as income minus the production cost minus the storage cost. With our new decision variables, the objective function can be denoted by the following expression. The first row is our total income, which is obtained from the number of units sold during the 6 bimesters, multiplied by the selling price. The second row is the production cost, which is obtained by multiplying the number of units produced each period, by the cost of production in each period. The third row shows the storage cost, which is obtained by multiplying the number of units held in inventory at the end of each bimester, by the cost of unit storage. Now, let me show you the constraints. In the first bimester, we will have the following constraints. Our first constraint says that, in the first bimester we cannot sell more than 1,200 units. The second constraint tells us that, in the first bimester we cannot produce more than 2,500 units. The third constraint states that the units that will be stored at the end of the bimester, will be the difference between our production and the number of units sold. Note that this constraint ensures that, the number of units sold is less than or equal to the number of units produced. This is because S1 plus H1 is equal to P1, and H1 is greater than or equal to 0. The fourth constraint refers to storage capacity. The number of pieces that can be placed in inventory, does not exceed 3,500 units. Now, think about the constraint for the second bimester. The second period constraints, are very similar to the first set of constraints. The first constraint refers to the demand for the second bimester. The second constraint refers to the production capacity. The third constraint states that the units that will remain in storage at the end of the second bimester will be the difference between our production and the number of units sold, plus the units that were saved in the previous period. The fourth constraint refers to the storage capacity. The number of parts that can be placed in inventory, including our production, cannot exceed 3,500 units. Now, think about the constraints of the third bimester. The interpretation of these expressions is similar to those of the previous period. I suppose you can deduce the constraints for the last 3 bimesters. However, let me show you the complete formulation of this problem. Remember that on the left side are placed those terms that contain variables, and on the right side only the constants are placed. The solution to this problem is as it should. The solution is the same as the previous one. In the classic formulation of this type of problems, constraints are regularly formulated for one period, and the constraints for the later periods are similar. I hope this video has been helpful. Well, see you soon.